So Alex kind of spoke about the spatial distribution of these fish in thermal refuges, but we got to think about time as well. And on this presentation, it's based on those underwater images you saw from Alex over 2 years. Myself and Tommy in this area have been working on this. So we're looking at how time and frequency are bending these behavioral thermoregulation temperatures for Atlantic salmon. All right. Simpleton. All right. All right. Come on.
I made the click on the presentation because of the thing.
Okie dokie. Okay, there you go. All right. Okay, thank you. So just by way of overview then, first I'm going to speak about what behavioral thermoregulation is, what it looks like. Alex spoke to this already, so he's kind of done a bunch of the work for me, but I'm just going to reframe it again. Then I'm going to talk about a conceptual framework that we've used, and it's about hysteresis. I'm going to break this down for you because I'm assuming, well, folk may know what it is, but some folk may not. So I'll go through what hysteresis is, and then basically testing this conceptual model in the Miramichi over 2 years. And then obviously go into the results and discussions, and then work that we've planned for 2022. Elise Collette's going to start her master's on this, which is co-funded by the MSA, and that will basically look at these behavioral mechanisms we see in different temperature gradients. All right, so most simply, during extreme summer temperatures, Atlantic salmon will use cold water refuges. So this is what, maybe this will work. Can you press play on that there? Just on the image there. Yeah, so this is from 2020 at Parks Brook, another thermal refuge that the MSA augmented. It's just wild, like how many fish were there. This wasn't even as big as the one Alex saw in 2021, this is from 2020. And if you can go again there. So this is what it looks like when the fish have left the refuge, no fish there. And it's amazing that in some of our images, we literally have images every 10 minutes and they all just turn up in 10 minutes. It's wild. I don't know what's driving the mechanism. It's something that we're going to look into as time progresses. Okay. So this is another example. Again, you've seen this in Alex's presentation, but this is Black Brook here. So this is adult salmon during a thermal aggregation event. Here's when the temperatures have dropped below thermally stressful conditions. And again, they're back in the same spot. So this is what it looks like between juveniles and adults. So the onset, which Alex spoke to again already, done a lot of more road work for me here, good job, is that the onset temperatures differentiate between adults, 2+ fish, 1+ fish, and young of the year. Additionally to that, the onset temperatures can differ dependent on the river you're from. So this is work by Corey et al. From 2020, and they found that the temperatures that were leading to onset aggregations in the Southwest Miramichi was 27.3 or 27 degrees Celsius thereabouts, and in the Well River in Quebec it was 28 degrees Celsius. So we have differences, geographic differences, and what's interesting here is this river is more northern than this river. So the whole idea of latitudinal shifts now needs to be questioned. We need to start looking at what I would call a waterscape, and that's what Elise will do. So further to that, then we have this kind of observation. So this is from Cindy Bro at 2007, and what you can see here is that there's variance. They were seeing aggregations of juveniles and temperatures got to 24 degrees Celsius. So again, this kind of contrasts what Corey et al. Saw. So Southwestern Miramichi got 27 degrees Celsius, and then in the Bro paper, they've got greater than 24. So which is it, 24 or 27? Pretty important question. 3 degrees is a lot, right? So the question becomes, why is there variability there? All right. And this is me before a coffee and after too many beer. Okay. So let's pause there for a second, take a sidebar. So what is hysteresis? So hysteresis is simply, I hope this becomes simply when I explain it, the state of a system depends on what has happened to the systems in its past and then what's happening to the system now. So system, a bit of a knobby way to say, let's just think about a fish. Or we could think about a runner. Actually, so sorry to be such a pain in the ass again. Can you move that up to the top there? I'm a nightmare, but yeah, because I do need that bottom part. Very sorry, I'm sorry. Okay, so thank you very much, right on. Okay, so if we consider a runner here, and the runner is Usain Bolt, all right? Here we go, potentially. Thank you. Okay, so let's say Usain ran a lap and he's killing it, right? So he does 100 meters in 9 seconds, just kills it. If Usain ran again in 30 minutes time, what would you expect would happen? Would his lap time be faster or slower? Why? That's thermal hysteresis. So basically, him running prior has an effect on what is happening in the present, right? So if he runs it again and again and again and again over a certain window of time, we end up with longer and longer lap times. So it takes him longer to get to finish the race. Usain's going for it there. All right. So what if Usain took a couple of days off? What would happen is lap time. So if we consider again the exact same, this is where he starts. So this is the last run of the repeat lap. If he goes in a day's time, rather than 30 minutes time, he's going to basically bring that time it takes him down again, right? So it's going up and then it's coming back down as he basically rests out. So over 3 days, then his lap time is to what it was prior. So it's basically come back to that initial state, right? So that's hysteresis. So we have here for fish, we have a force, and the force is temperature, right? So we're temperature fluxes, so we're pushing the force in the system, temperature here. And as the temperature changes, you have a change in strain or physiological stress, although this is, so I'm going to have a sidebar here. This is what I don't like. I'm not a biologist, so I don't like this about biologists. They say stress, physiological stress, but it's actually a strain response. But I'm going to stick with this knowing that it's incorrect for biologists. All right. I'm saying that for my engineer mates that watch this and they're like, you're an idiot. I know that. I don't need you to tell me. Anyway, so, okay, so let's say we have this instance here, right? So here we've got 0.1. And at this point in time in 1, basically the temperature starts to increase. And as that increases, we're loading the fish up with stress, all right? So as it gets to this 0.3 here, it's basically, this is the point in theory or conceptually that it will go seek out a thermal refuge. So once it's in that thermal refuge, then it starts to basically unload because it's in a colder temperature, strain, physiological stress or strain starts to drop, all right? So this is our conceptual model, hysteresis, comes up here, bang, and down. However, fish are organic organisms, right? So this is the thing that we're talking about here, the unloading part. They can repair themselves, all right? So hang in with me. We're almost out of the reads here and we can actually get into stuff that's meaningful. So again, we have this thermal recovery model up here. So if we think about this, oh shit. Okay, sorry. Okay, so we have this force on the y-axis and the strain on the x-axis. So let's say we have an event. And so this is basically the amount of time that has passed since the event. I've said low and high. It's kind of a weird thing to say, time since the event. I don't know what's the proper word to say for this. But let's say we have had a long time. So we have this 0.1 here, right? So this is the initial point. We have this loading where the temperature increases and bang, the fish goes into the refuge. Okay, now we're starting to unload again. But now we've had another event within a day. It changes the hysteresis loop. So bang, so now it's going at a lower temperature than before. So basically you have this whole movement here where you can see the frequency, or excuse me, the time since the event will change the temperature at which they seek the refuge. Does that make sense, or am I talking total bubblegum? Carol, yeah, thank you, darling. All right. So I'm going to go with Carol saying it's fine, and that's fine. Okay, so more simply, it looks like this, all right? So we have an aggregation onset here, and basically as the time since the event occurs, we have this recovery curve, all right? So it can't recover forever, so it basically asymptotes are basically it plateaus and it can't reach any higher than that. So it's not like Usain Bolt is not training all the time and dropping its lap time. It basically hits a ceiling, all right? So we want it up to that ceiling. So that's the recovery part. But now we got to think about the reduction part, or Usain running around the lap every 30 minutes, all right? So here we basically end up with, I'm saying basically a lot. So here we end up with the inverse of this curve here. So if we have recovery, the inverse of recovery is going to be reduction, all right? So the reduction curve mathematically is going to be the inverse of this. I'm not going to go into the maths, but it just, trust me on that, it's the inverse of it. So here we have the frequency of events. So let's say we have the first event here, and we have this loading curve this way for the stress, again, the inverse of this. And this is the temperature we're going to seek out refuge at. So we come back down here then, it's starting to unload, and then we have another event. So it drops the temperature which they seek refuge. And then it keeps on going on this loop here until you have really high event frequency, over a certain amount of time that will really reduce the temperature at which these fish are going at. All right. So my point to this is it's not static. The fish is a function of the river it's sitting in, a function of the temperature. The temperature goes up and down, the fish gets fatigued. This is important, right? And then if you think about that loop, it's gonna have to be some exponential because it can't be linear, otherwise it will go on forever, the fish is gonna die. So there's gonna be some limit to how much thermal stress the fish can take before it dies, okay? So this is just basically sealing the hysteresis loop then. Okay, all right. I don't know what I was saying there. Okay, so we can represent that mathematically then, all right? So I'm not going to go into it in too much detail, but in most simple, if we have an event really close together, we're going to have a lower thermal aggregation temperature, and then as the time since the event increases, we go back to what we were prior. Same thing here with the reduction of it. So here we have a low frequency of events, but as we increase the frequency of events, we end up with lower aggregation onset temperatures. So this is what's happening conceptually. And then we can blend these things together and basically say this plus this is going to equal this. And you can basically account for, again, basically, you can account for everything here. All right. Okay, so just to give an overview of the study site, we have Parks Brook here in 2020, it's cold water refuge. This is the little southwest Miramichi, flow direction is going this way. And then we have Otterbrook in 2021. The reason that we have Otterbrook in 2021 and Parks in 2020 was in 2020, we put cameras in Parks. And then in 2021, we put them in both Otter and Parks. And there was a hurricane that came through, I think, a tropical storm, and it basically filled Parks Brook in with a meter of gravel, buried our cameras. So we didn't have any data for 2021, but what we could do then is we use this Otterbrook data here. So here's the thermal plume that Alex showed you. Here's Parks Brook. Parks Brook is much, much shorter than Otterbrook, and this is the position of the cameras. So we have a temperature logger here in the main stem and one on the camera here, temperature logger here in the main stem and one on the camera here. And basically you see the differential between the thermal refuges. To come back to this point, so Parks Brook ended up being our test data set. So we built a model from the 2021 data and then we tested it against 2020. So the reason behind doing that was twofold. Number one, we have more data from 2021, but number two, 2020 is independent of 2021. So using that hysteresis thing, even though you'd assume over a winter, these fish are going to reset or whatever, we want to offset any tether through time of those samples. Okay. So we built these underwater cameras in 2020. They were capturing 30 seconds of video every hour of the day. So these are passive sensors. They can only work when we have sunlight. So they only capture imagery between 5 and about 9 o'clock at night. All right. 2021, these were very glitchy homemade cameras. So we went with these guys here and they basically gave us a photo every 10 minutes of the day for the same time period. So much higher temporal resolution. And then we had to define what an aggregation is. So we said that an aggregation is any time we observe over 10 Atlantic salmon par in an image at one time. All right. Okay. And then we have to also speak about what we define as an aggregation. So there's instances when we have an aggregation and it lasts for 2 days. All right. So they're in the thermal refuge for 2 days, but we have to classify these as unique aggregations if we're trying to pick out this hysteresis. So what we said was a unique aggregation is one which occurs after the one prior is broken up, right? So it kind of makes sense. Okay, so what's the story? Stuff here. Sorry. Okay, so in 2020, the cameras were glitchy. It gave us 10 onsets or unique onsets that we were confident in. And what I mean by glitchy, in August of 2020, which was the hottest as well, the camera started turning on and off randomly. And I looked at the code and I don't know what was going on with it. So we have to discard that data because we have lack of confidence in it. All right. So this is why I went to the 2021 cameras where they work beautifully. They work really, really well. So again, so this is the training data then, this is the test data. So between the 2 years, we have n is equal to 17 unique aggregations. We have a total of n is equal to 19 observations, but we need to withhold 1 each year to set the baseline. If you have questions about that, I can answer later on. Okay, so just an overview then of the thermal characteristics in both years. So here's the river temperatures. So in 2020, Lower water year, look at the difference. Lower water year, we have 29.7 for the maximum temperature in the main stem. 2021, higher water year, maximum temperature is 31.5. So that's another paper I'm working on where what happens is if you have groundwater coming in, it becomes dominant during low flow conditions, it actually buffers the river from extreme temperatures. So this is really counterintuitive to what you think would happen. The thermal plume, so this would be Parks Brook and then Otter Brook. Parks Brook is warmer than Otter Brook by about 1 degree average, and then about 1.5 degrees for the maximum. So that's going to be important in a moment. And then for the onsets, this should be n equal to 12 here. Sorry, I just finished this morning. So for the onsets, we can see that we have an average onset temperature for aggregation is 26.5 in 2020, and then 2021 is 26.2. Maximum is about 27.1, which is bang on in line with what Corey et al. Are finding. And then the minimum temperature in 2020 is 26.1, with a caveat here that we're missing out that August data set from 2020 when I think it was the 8th of August, the river got really, really warm and we had big aggregations in the video. We did not know when they began, so we can't use them. And then for the lowest in 2021, we have 24.2. So these numbers should look interesting because it's what Bro found and then it's what Corey found. Okay, so just towards observations then. So the gray line here is the maximum temperature of the river in, let's see here, yeah, in 2020. And then the black line is the maximum temperature of the river in 2021. So it baked. So Alex, that day he was there, Friday the 13th, was the warmest it's been in that 29-year stretch. So 31.5, it was just baking. The interesting thing here is the thermal refuges. Otter Brook is colder than Parks Brook. And the reason it's colder is there's an esker to the west part of Otter Brook, and it's 14 meters deep, holds a lot of water. So that drains off into the wetland as groundwater, and it gives you that really temporally and thermally stable refuge. Parks Brook is not. It's located with shallow superficial geology, and it's in a deep water classic, but it's not very incised there. We can talk about the mechanisms if you want, not important. Anyway, so here you can see, thank you so much, you're on it.
If anyone knows how to get rid of
How to get rid of me is just tell me get out. No, I'm just kidding. Okay, so here we have the unique aggregations. So you can see here that we have the first aggregation, the first aggregation that occurred in 2021 happened on June 8th. So that's pretty incredible. And in 2020, it happened on June 19th, which is my birthday, which is also pretty cool. Excuse the pun. So then we see for the gray dots, that's 2020. In this blue area, this is where the camera got squirrely. In this blue area, I also want you guys to look at this here. So this is kind of showing what we're predicting is happening. There's something going on here with frequency and the decay of the onset temperature. Okay, so we built these models. We have a recovery model, we have a reduction model, and then an integrated model. So that's those models that we spoke about earlier on. These work quite well. The recovery model, not so much, and we can get into the nuts and bolts of that. But the reduction model predicts the aggregation with an R squared of 0.9 and an adjusted R squared of 0.89 and a root mean squared error of 0.3 degrees Celsius. So I build stream temperature models quite a bit, and I've never gotten them this tight. This is really nice. And even for the reduction model, excuse me, I'll start up here. For the recovery model, the arcs kind of falls out of it here, and I'll get onto why that might be. But the reduction model seems to be quite consistent through space and time, that we have a test R squared of 0.7 degrees Celsius, and the root mean squared error is almost identical to what it was in the year where we built the model. So this gives us a bit of confidence. When we integrate it, so when we close that hysteresis loop, we get a really strong adjusted R squared, so 0.9, and the root mean squared error drops to 0.25. And then for the blind year, it's 0.81. And again, the root mean squared error is 0.28. So this to me now, I'm like, okay, I'm happy. There's something here with two parameters that we're picking up on. So this is important. Okay. So just to look at those curves again, you're grand, don't even worry about it, we'll just flow with it. So here's the recovery model, and you can see that like we thought, we have this curve this way. So for the 2020 data, which is the black point, the training model, we have an R squared of 50, root mean squared error is 0.6. So this model is not as robust as the reduction model, which we have here. You can see this is a really nice relationship in both. What might be happening here? So the recovery model, the fish are occupying two different refuges, right? So even though the main stem temperature, they're only 10 kilometers apart, the main stem temperature is one thing, but it's the temperature of the refuge that they use is really important, right? So Otterbrook is colder than Parksbrook. The fish that utilize Otterbrook because it's colder they're going to be able to recover faster than the ones in Parks. So now it gets tricky because now we're not even talking about river by river management. We're talking about reach and the thermal refuge, right? So you got to think about the longitudinal variation of the temperature, and then you got to think about what's coming into the river. So think about adult salmon, Black Brook, honey hole, right? Epic salmon's fishing spot. Fish, that's a really cold brook. And if you compare that to, say, Big Hole Brook, which is a bit warmer, in theory, for the adults, it should follow through the same mechanism that the fish that utilize the Black Brook thermal refuge will recover quicker because it's a lower temperature there than what we see in Big Hole Brook. So now think about what Mark and what's Buddy's name there? Sorry, what's the other guy's name? Travis, right on. Okay, Mark and Travis presented about the catch release stuff. I would imagine that we're going to see differentials in our rivers based on not just the temperature of the main stem, but the refuge where the fish use, right? So that's going to be important. So what happens when we account for the hysteresis, we get much stronger models. I'm just going to go through this. So it becomes three-dimensional. We got to take into account this event frequency, this omega function here, and this lambda function here for the amount of time that passes. This is maybe over people's heads now. The point is that when we blend those two things together, we get a much more robust model, all right? So take-home points, the thermal thresholds for salmon parr are highly dynamic. That means that we can't have a set boundary of which we close the river down or whatever. We have to move with the river, all right? So we should not be using a simple temperature for management. And I suggest, and I hope Tommy would agree with me, that the thresholds ought to follow the river temperature. And again here then, we conceptualize the recovery thresholds are going to be dependent not on the main stem itself to a degree, excuse the pun, but the temperature of the refuge. That's going to be really the key thing here. Also, I want to say that Jason Curtis has lovely eyes, and you can see his eyes here in this photo here. It's him down there.
Too lovely.
They're too lovely to show anyone. Okay, so we're just scratching the surface here. And this is Elise Collette. Elise is going to start, she was a Fenity Scholarship winner, and she's going to be starting on looking at putting these underwater cameras in different thermal gradients to see if the mechanism matches, but then Elise can build a model that captures a thermal variability, so we have a mechanistic model that's transferable to different areas. And we're also looking at adults, so stay tuned. So a couple of folks I want to thank, Ali Pugh, Mikey Rickard, and Alex Morgan helped me collect this data, and we have a bunch of funders, so thanks for that. And if you have any questions, I'll try to answer them.